day, folks. This is Jeff Snow with Anderson-Negele. I'm the Distributor Development and Field Service Manager. I've been traveling around and visited with a lot of you folks, and one of the presentations I've been doing lately has to do a little bit more with process, including product, and a little bit less about just the product. And I thought I might do that with you today. So what I'm going to do is a kind of a shortened version of our CIP process overview, where I'm going to tell you about how a very typical CIP system works, and you know, why it works the way it does, and what the cost of running a system are, and how we can help a customer save some time and money by measuring the correct things. So we're going to kick that off here. We've got looks like the level of people joining is steadied off. And what I'd encourage you to do is I'm going to keep an eye on the chat and the Q&A. If you have any interaction along the way, go ahead and chime in. I'll try to watch for it, and we'll see if we can involve your comments along the way, and maybe make this a little more interactive. All right, so we will get things started here. So we're going to basically talk about the instrumentation used in a CIP process. This is a typical food and beverage CIP process that we tend to see here in North America, which is where most of my experience is. So this is what we're going to talk about. The products we're going to cover during the CIP are listed here on the screen. We're going to get through a number of them. We'll go into a little more detail on some than others, but you know, we're going to talk about the level transmitter, conductivity, turbidity, flow meters, flow switches, and even the temperature sensor, and as well as just how the CIP system works. So I'm jumping a little bit ahead here. My pointer's kind of jumpy. So first thing, we're going to look at the CIP system, and hopefully this looks a little familiar to you and you recognize it. This would be a single tank CIP system, and if you, there's my pointer, if you follow it through, you know, we've got basically a tank of water, and we are going to circulate it. We're going to add some chemicals to it. We're going to measure things. We're going to heat it. We're going to send it out to something we're going to wash. Right? Then that water is going to come back. So this is what that CIP system looks like. I often compare this to just, you know, washing dishes, right? You've got things you've got to get clean. If any of you are brand new to this, sometimes we have some brand new people. CIP is clean in place. It basically means that we're not going to take down our piping and our valves and our tanks all apart. We're not going to go in and scrub everything by hand. We're going to build it and fabricate it in such a way that it can be cleaned while left in place. So as it's being used, we're going to circulate water, warm water with chemicals through it. And because of the design of the instrumentation, of the pumps and the valves and the piping, it can be cleaned that way. So it's CIP-able, right? So it's going to meet, in a dairy, it would meet 3A standards. In Europe, it would meet an EH standard. It's basically going to be designed so that there aren't little nooks and crannies that are going to kind of shelter any bad things, any bacteria, and that the CIP system, the solution, can wash it. So the idea is here that we're going to leave everything in place, and we're going to clean it. You know, I'm going to go back to the dishwasher analogy. This would almost be like you put your dishes on the table, you put all your silverware out, you put your glasses on the table, you eat, and then you get up and you walk away, and this machine just comes, instead of you taking the dishes to the dishwasher comes to the table and it cleans everything in place, right? Now, that wouldn't make a whole lot of sense in your dining room, but if you think of a processing plant where we've got all this equipment, tanks, valves, pumps, process lines, mixers, just all kinds of things, heat exchangers, it is not practical to take all that apart and carry it to the dishwasher, right? If we did, that would be what we call COP. That would be a clean out-of-place process where we're taking all the equipment apart and we're kind of washing it separate. We're going to clean in place, so we're just going to leave everything where it is, and we're going to get the cleaning solution to it. And that's what this process is all about here. So get some water, put some chemicals in it with this chemical feed pump, circulate it at a certain flow rate, measure some things as it goes, heat it up in the shell tube heat exchanger, and send it out to whatever it's washing, right? Then once it comes back, we're going to monitor some things, and we're either going to send it to drain or we're going to put it back in the tank. This drawing here would be a single-use or single-tank CIP system where everything comes out of one tank. And what that means is anytime you switch from fresh water to chemical, you know, caustic or acid water, you actually would need to add that, and then when you switch back to rinse, you have to drain it, get fresh water in there. So lower price of investment in a single tank system. If it's a single use, that might make sense, but a lot of times we're going to have a multi-tank system. So what exactly is a CIP system supposed to be doing here? What's the cycle that we're going to be looking at? Well, first of all, we need to kind of run some water through there and rinse out most of those solids. Compare it to washing dishes. You know, a lot of times some of us will rinse our dishes off before we put them in the dishwasher. If you ever open your dishwasher during its first cycle, you realize the soap dispenser hasn't opened yet. It's going through a pre-rinse step where it's just kind of rinsing off most of the solids. So a CIP system is going to start by pre-rinsing with fresh water to get rid of most of the solids. We don't want to recirculate those solids. We want to get them out of there, so they may actually just go to drain. Then we're actually going to do our wash. This is where the soap dispenser in your dishwasher opens up. We're going to put some chemicals in there. It's going to be a caustic or a detergent type wash, and we're going to heat the water up. Right? Our dishwasher doesn't run cold, at least it shouldn't. We don't wash dishes in cold water generally, and we know that heat or that temperature helps break down what we're trying to clean, so we want that step. So that's the wash, and we're going to recirculate at this point because it needs to happen for a while. We're going to rinse that out. We may go back to an acid wash, rinse that out, and then we may finalize with a sanitize. So really, really basic here. These are the steps of a basic or standard CIP system. What are we trying to accomplish here? Have some of you heard the TACT, or if any of you have been taught CIP before, you may have been taught this TACT. Anybody know what it stands for? Give you a minute here to respond. Somebody go ahead and be bold and put it on there. I'm the only one that can see your responses, so if you get it wrong, don't worry. All right, so TACT is something that Sanomatic will teach, and I've heard it taught at other places, where it's time, action, chemical, temperature. Those are the things we're trying to accomplish with the CIP system. We need to have the washing occur at a certain temperature. It needs to be warm. We need to have the flow rate or the action or the turbulence, right? So when we're washing dishes, we're scrubbing or we're using a sprayer. When it's in the dishwasher, we've got nozzles in there that create some pressure on the plates and the things we're washing. That's where the action comes from. We don't wash with just fresh water. We wash with some soap or some chemical. So there's a chemical function. And we also can't just, spray a little water on something, put a little soap on it, and have it magically become clean. That's got to take some time. We've got to kind of erode those soils away. So we've got the time in there. So temperature, action, chemical, time are all the things that are critical to make a CIP system effective, right? That makes sense. You've probably heard that before. It aligns with what a dishwasher does or what you do when you wash your dishes at home, right? It's got to be warm. There's got to be some scrubbing action. There's got to be some sort of soap or chemical in there, and it's got to be there for a certain amount of time. So all those things are necessary to make a system work, but if you ever think about when a customer is using a CIP system, they're not processing, right? So a customer is making money when they're processing. When they're turning raw materials into finished product, they're processing it, they're cooking it, they're mixing it, they're blending it, they're doing whatever it is they do to it, pasteurizing it. That's kind of where they're adding value to that raw material and they're making product and they're making money. When they shut down and they have to wash, guess what? It's a necessary step. They have to do it. They have to shut down and wash, but they're not making any money. Again, go back to being home. When you're cooking a meal, you're bringing in all these raw ingredients, you're processing them, you're cutting them, you're cooking them, you're preparing them, you're serving them. That's all what you and your family and your guests are there for, is for that, right? When you're all done, everybody leaves the table and you got this big old mess to clean up. Nobody wants to deal with that. It's just a necessary cost of making that meal. And that's how a processing plant works. CIP is just a necessary cost of the processing. If they could minimize the amount of time and the amount of money they spent doing it, that would be that much better. We make a big meal. If we didn't have to clean up after it, that's the best part, right? That's why we like going out to eat, because we don't have to clean up afterwards when we're done, right? So there are some costs in operating the system. We've got the steam that we're using to get our heat. We've got this chemical that they're buying from a chemical supplier. If we have any chemical salespeople on here, they're probably going to come and kind of whack me because they don't necessarily want this story to be told, but those chemicals cost money. Do we really need to use that many chemicals, right? Are we putting chemicals in water that we don't really need because we've got too much water, right? So there's a cost to the chemical. The amount of time that we're spending cleaning isn't making the customer any money, right? So if they run 24/7, they want to be processing as much as they can. If they have to shut down to wash, well, they're not generating revenue at that time. So time is a huge factor. If it's a smaller scale plant and they process, they shut down and they clean and everybody goes home, The time has a little bit less to do with the revenue generation. It just means they get to go home a little earlier. But in a lot of the bigger plants these days, they're just running nonstop. And so stopping to clean is just something that costs money. And then we've got the water usage, right? We don't want to be wasting water that we don't need to. There is some cost to that. There's also some cost to putting that same water down the drain. But especially if you're on the West Coast, we can appreciate how much we really don't need to be wasting water if we don't really need to be using it. So those are the costs of operating the system. If you're kind of curious about, well, how hot does the process need to be? How much turbulence or how fast does the water need to flow? What are the chemicals? Here's a slide that kind of answers some of those basic questions for you. Temperatures around 150 degrees, 170 degrees, something like that, depending on the process. Generally, the acceptable flow rate is 5 feet per second. This is what we're looking for to get the turbulence we need. Generally, we're using some sort of caustic soda detergent to remove the proteins that we're cleaning, and then we may come back with an acid to remove the calcium, especially in the dairy. And generally, we're washing from 20 to 40 minutes on the caustic and somewhere around 10 minutes on the acid wash, right? Just to give you a rough idea what some of the details are having to do with this. So we go back to our single tank system. We talked about how that one works. Suppose we wanted to not dump our wash water and our soapy water, our chemicals, every time we change cycles. Well, we could put in a second tank and have a rinse tank. So here we have a wash tank that you can see the circuit is set to recirculate through. Right, so we're going to go out, we're going to come back, and we're going to go into the wash tank, and we're going to go around, around, around. And then over here we have a rinse tank, which is always fresh water. So here's my fresh water coming in. The return line does not go to the rinse tank. This way, when I switch from a wash to a rinse or a rinse to a wash, I just open the other valve. I don't have to drain the tank and change out the water. So this speeds up the process quite a bit. What else can we do? We can actually put a third tank in. You see these quite often, and generally we call it a rinse recovery tank. What we'll do here is we'll take the very last rinse from the previous wash and we'll capture it and we'll save it or we'll recover it. Have you ever kind of cooked a big meal and you wash the dishes before dessert and then you got that kind of nasty, soapy, warm water and then you've got the next round of plates to put in there and you just kind of put it in that nasty pre-used water, but it's got some soap in it and it's got some temperature to it, and I don't really feel like washing dessert dishes right now anyway, so I'm going to throw them in there. That's kind of what this rinse recovery is doing here. So I've got some water it's warm, it's got some chemical in it, it's been used to wash other dishes. I wouldn't call it my final wash, but I can actually use that to rinse the next cycle through. And that's what this is kind of doing here. I'm soaking those dirty dishes in this water that's already a little bit dirty, but it's going to help start getting them clean. And plus, I've already paid for the soap in that water. I've already heated it up. Why not use it a little bit more? So by capturing the last rinse of the prior CIP cycle, I can run that through my first rinse of the next cycle and get some of those soils out of there without having to put more heat and more chemical in like I would if I use the wash tank. So that's kind of why we see a rinse recovery tanks. Help save time, optimize the processing time, uses a little less water, a little less chemical, and less heat. All right, so let's get to the instruments. I promise you we're going to talk about the instrumentation here. So we're going to put some level sensors in these tanks. It is not uncommon to have point level switches in CIP tanks, and a point level switch is going to turn the fresh water, right? Fresh water coming in here, it's going to turn it on and off, and it's just going to maintain a working level. If you ever look at a point level probe in a CIP tank, how many probe lengths do you generally see? Usually it's 3, maybe 4, but generally what we have is a high level, low level. So turn the water on at the low level, turn the water off at the high level, and then a high alarm or even a low or empty tank, basically, which will shut it off. So depending on if it's 3 probes or 4 probes, we're kind of maintaining a working level, and then we don't want to run the tank out. That would be a 3 probe. But you're always going to be running at the same level. You're not really optimizing your water usage or your water level at this point. You're just using as much water as those probes were cut for. So one of the ways we can help a customer save time, money, water, chemical is by putting a continuous level sensor in the bottom of the tank and measuring the working level in each tank based on the circuit that we're washing. All right, so put a level sensor in there. It's a continuous level sensor. It's giving a signal that's proportional to the level. That's going to go back to the PLC, and we're going to bring water back into the rinse tank as we need to. Rinse tank, we don't really worry about precisely where the level is quite so much, but when we get to the wash tank, it's a little more critical, because if we put more water in the tank than we need, then we have to put more chemical in it to make up that concentration. We also have to heat that water, and all those things come at a cost. Now, if you only ran this cycle once a month, this probably wouldn't amount to anything and it wouldn't be worth it, but when you're running multiple CIP cycles per day, you're using a little bit more water, a little bit more steam, a little bit more chemical each time. Anything we can do to save that is going to help save us money in the long run. So by continuously measuring the level in the wash tank, we can help our customers save money on chemical and time and water and even steam. All right. Down below, if someone wanted to say, well, how do I know that this level transmitter, and by the way, it's the L3, which we've talked about before, how do we know that this is suitable for this process? Is it 3A? Is it going to withstand the temperature? Does it have a signal that my CIP system is going to accept? That's where we're listing the specifications out here, basically saying, yep, it is a suitable instrument for a CIP process. Your automation engineer is going to be able to take the signal. It's going to go into their PLC just fine. It does meet 3A. It's going to withstand the temperature that we're going to see. It's going to withstand the chemicals, and it's got process connections that are commonly found on a CIP tank. So an L3 would be an ideal level sensor to put at the bottom of a CIP tank and measure that temperature. And if any of you have seen some of the earlier presentations on the L3, you know about how stable it is with regard to temperature. So we're not going to see any shift based on the CIP temperature the CIP cycle water getting hot. All right, and then how does it work? So real quick slide on how the L3 works, basically hydrostatic pressure. We're not going to spend a lot of time on this, but if you look at it, you'll see that as pressure, as the level built up in the tank, it's exerting pressure at the bottom of the vessel. The more pressure, the more level. We can use that to determine the amount of volume in the tank. All right, I'm not going to read that whole slide to you. Moving on from there, we might put a pressure transmitter at the discharge of the CIP supply pump. In the old days, before we had flow meters on CIP systems, this was very, very common, just to know that the pump is running and we were generating pressure. If you look at an old CIP system, you might see a chart recorder on the return temperature and on the CIP pressure. So this would be that pressure here, and what we're really going to use it for now is to monitor that pump. Right, so we'll put a pressure transmitter here. Guess what? L3, pressure and level transmitter, does the same application. We're going to monitor the discharge of that CIP supply pump, make sure it's doing what it's supposed to, compare it to what it normally looks like, so the PLC can recognize if something's going wrong. You might have noticed a strainer on that right afterwards, so it's quite common to have a strainer on the CIP supply line. If that strainer starts to foul, we'll see pressures that are not normal there, and the PLC can alert us to what's going on there. So good place for a pressure transmitter on our CIP system. Very, very common to have it here. The next thing we talk about is the chemical. Right, so we not only need to maintain some pressure on the line, maintain level in the tank, but we need to put some caustic and some acid in there. So we've got a chemical feed pump and a drum. And how do we know how much chemical is put in there? Well, we do know that when we put chemical in CIP water, it changes the conductivity of the water. It changes its ability to conduct electricity. So we can put a conductivity sensor in the CIP supply line and use that to control the CIP system, the chemical feed pump. So this is our conductivity. This would be the ILM4. We do know that the conductivity is proportional to the wash chemical concentration, and that's a repeatable relationship. So we can program our PLC to maintain a certain chemical concentration and then optimize the amount of chemical we put in on the supply side and ideally control that chemical feed pump to get that concentration going out. If we're not putting in too much or too little, we can optimize our wash time and optimize our chemical usage. All right. So how does the ILM work? Some of you may have seen this from us before. We've got a toroid, a coil, all right, a wire-wound coil that creates creates a magnetic field. As the conductive media is allowed to enter the core of this field, it's going to transfer those lines of flux to a receiving coil. It's going to induce a voltage on that coil, and that's going to be interpreted by the circuitry to determine the conductivity of the sensor. So there's basically an opening here where the liquid will go inside. It doesn't have to be flowing. That's not how the conductivity sensor works. That's how a magnet works. The conductivity sensor just looks at how conductive the media is. Temperature does affect this, so we do have a temperature sensor down inside that toroid as well. All right, we can look at the specs of this. There's some kind of neat things we can do with the ILM with regard to its adjustability and its programming and its wide rangeability, so we can look at the specs and talk about that. If we keep moving, we said we need to maintain some flow rate. right? So we're going to have some sort of flow meter on the CIP supply side to make sure that pump is putting out the correct flow rate. So generally that's going to be the IZ mag, and it's going to come back to the PLC. So the velocity, we said 5 feet per second is critical to proper cleaning. We need to know what that flow rate is. 5 feet per second is a linear velocity, so if I'm cleaning a 2-inch line, that's going to be one flow rate. If it's going to be cleaning a 3-inch line, then the flow rate's going to have to be even higher yet. So, you know, depending on what the circuit is, we need to optimize that flow rate. The signal coming out of the flow meter will be a 4 to 20 milliamp signal. It will go to the PLC, and the PLC will perform a PID calculation and will control the variable frequency drive that drives the pump to maintain that flow rate. In the field, you may see a vortex flow meter out there. We can replace that vortex flow meter with an IZ mag, or if we're building a new CIP system, we would use the IZ mag identical mount and measure that flow rate coming out of there. We also can take the pulse output from the IZ mag and bring that into the PLC and monitor our water usage by basically counting the amount of flow that's going through the meter any time that the drain valve is open, and then we know that we're using water, consuming water. Okay. The IZ mag works by creating a magnetic field across the flow tube. So there's coils on either side that create lines of flux across the tube. As a conductive medium moves through that magnetic field, it induces a voltage on the pickup probes, and then the circuitry interprets that voltage and can give us a signal that's proportional to the flow rate. And then here's the specs on the IZ mag so that we know it's suitable for a CIP system. Generally on a CIP system, we're going to use an integral mount. We're going to go with a low voltage. A lot of times this has to do with just cost. CIP systems, generally, when you quote one to a customer, you're probably not the only one quoting. It's generally competitive, so everyone needs to keep their prices in line. So we use an integral mount, use a DC voltage, and we can use that on CIP. All right, what else do we have on the supply side? Last but not least, we've got temperature. So this is a shell and tube heat exchanger. We're injecting steam into the shell. The steam is condensing and giving its heat up into the water that's flowing through the tubes. There's multiple tubes inside here, and we need to measure the temperature of that water coming out to make sure it's hot. We want to measure the temperature right close to the heat exchanger so we can control this valve so we can get the temperature we want going out on the CIP supply side. So this is going to be an RTD, which is generally our TSB or our TSM. You've heard me talk about those before a while ago. And so it's a temperature sensor or a temperature transmitter. Sometimes we are using a 40 to 20 milliamp output because that's what the PLC is set up to accept. All right, so we'll put a temperature sensor there. Again, TSBs, TSMs, if you remember some of my earlier presentations, we will offer these up in exchange or as a competitive replacement for other brands that might be out there that might be a lower cost than our SACT. So if for some reason you're looking at SACTs and you're looking at the price and saying, well, that's probably not going to help me be competitive, don't stop there. Look at the TS and then look at our promotion or that we've run, or if you've received a message from me before, we will offer a 60% discount on TSMs and TSBs just to basically let you use that instead of a pyramation. Okay. All right. Everything we just talked about was on the CIP supply side. So that's the water going out to whatever we're washing. Now we're switching over to the CIP return side. I realize I'm running a little long on time, so I'm going to try to keep cranking along here. When we send hot water out, we send chemical out, we send flow out. We don't know that everything that we're washing is truly seeing that flow rate, that temperature, that chemical concentration if we don't also measure it on the return side. We need to see it coming back. So we're going to put instruments on the return side of the CIP to ensure that everything that we sent out has fully had a chance to do its job out there in what we're washing. So if you think about it, you've got cold piping, you send hot water out. Do you think it's still going to be hot when it first comes back? Definitely not. It's going to be taking some time to warm everything up. So we really can't say we start washing until we have hot water coming back. So let's work these sensors one at a time and see what they're there for and what they do. First one is a flow switch, and we're going to put that on the return line to make sure that we know product is coming back. So any of you have been in a plant, you see how a CIP system gets hooked up. It is very, very common for operators to need to move some swing elbows, shift some valves, shift some flow verters, sometimes even hook up some hoses. out on the process equipment so that the CIP flow comes back. If they don't hook it up correctly, the CIP flow isn't going to go where it needs to go, and it may not even come back to the CIP system. So how do we know that the circuit is complete? Well, we'll put some sort of flow switch on the return line. So the FTS741 is our calorimetric flow switch, and it's going to give us a signal that lets us know that we've got flow coming back on the return line. All right. If flow doesn't come back, generally what will happen is the PLC will be programmed to stop the supply pump and set off some sort of alarm to warn the operator that, hey, you need to go out and figure out what's wrong because it's been a couple minutes and your water hasn't come back, so something's not quite right. So this is the FTS741. This is a new version that is just basically it's an upgrade. It's not really a change. The part number didn't change. It's just a kind of a little change in the packaging, a different window, and a little bit easier to use user interface on this new STS741. So that's just going to be a running change on that particular product. So that's brand new news. All right, so that's the FTS741. How does it work? It basically works by putting a little heater in the probe and a temperature sensor sitting right next to it. And as the heater, this is the heater, this is the temperature sensor, as the flow goes by, it's going to pull the heat away. All right. I often compare this to if you're standing outside on a day that's not too sunny, you've got short sleeves on, and you're very, very comfortable, and all of a sudden there's a slight breeze, and you feel a little cooler, even though the temperature hasn't changed. And that's the wind pulling the heat away from your body. Well, that's what's happening here. That flow is pulling the heat away from this probe. So this red line is the heater turning on. The green line is the temperature coming up. When the heater turns off, the temperature starts to drop. How much the temperature drops is going to be proportional to how much flow is moving by. And that's how this is basically set up to do its switching. You know, depending on what this delta T is, this change in temperature will be related to a flow set point, and we can switch whether we've not got return flow or not. The FTS741 will measure between 1 and 10 feet per second, and we've got switch points throughout. We said CIP was return is at 5, so we're got an ideal range for CIP. We are not going to measure flow rates higher than 10 feet per second or 3 meters per second. The technology, basically all the heat would be pulled away at that point, so the technology doesn't support higher flow rates. But for CIP, it's ideal. All right. Also on the return line, we've got a turbidity sensor. So you may have heard me talk about this before or heard other people. We've been telling this story quite a bit lately. The ITM51 is a turbidity sensor that can measure suspended solids in water. The very first rinse on a CIP system is going to be the pre-rinse. This is where we're going to run fresh water through and we're going to get most of the solids out. And one way to do that might be to send them to drain. We don't want to put them back in a wash tank and recirculate them because we want to get them out of there. If we're putting solids down the drain, well, one, we're wasting some product, and two, if you're familiar with BOD charges, we're going to send these off to the water treatment plant, and the water treatment plant or the city or the municipality is going to send us back a bill for BOD charges. BOD is biological oxygen demand, and it's basically what the water treatment plant, or the water treatment plant, the sewer treatment plant, has to do to digest the solids that were put down the drain. So they have to feed oxygen to the bacteria whose job it is to digest these solids. When they do that, it comes at a cost, and they pass that cost along to us as the people who are putting those solids down the drain. So if you ask a plant engineer about their BOD charges, usually they'll kind of tell you a story about all the money they're spending on it, and if you offer to help them reduce that, that could be a big help to them. So this is a number that can be in the thousands of dollars per month for BOD charges if they're putting a lot of solids down the drain. That's not all coming from the CIP pre-rinse necessarily. There's a lot of places where solids can go down the drain in a processing plant, but this application here is specific to the CIP pre-rinse. So what we can do is actually send this pre-rinse, the first bit of solids out, put them in a salvage tank, and send them off to a hog farm or somewhere, and they spread them on their field or actually feed them to the hogs. So there's ways to salvage this and not put it down the drain. Also, if we're rinsing out all the solids, we don't need to waste as much chemical washing them out. And their alternative is, okay, well, I'll just rinse longer and make sure I get them all out. Well, now we're wasting water and time. So by actually measuring the amount of solids that are in the rinse water, ensuring that they're all flushed out and the water is pretty clear before we switch over to the wash cycle, we can optimize our timing, our water usage, and our chemical usage on our CIP system, which again saves time, money, chemical, for our customer, and reduce that CIP cycle time. And you can see the specifications here of the ITM51 that make it ideal. Now the ITM51 is a near infrared sensor. Basically puts infrared light out into the flow. The suspended solids reflect them back, and the receiving LED picks those up. And the more light that's reflected, the more solids that are in there. The circuitry interprets those signals, those raw signals, and converts them to a 40-20 milliamp signal that then goes to the PLC, so we can decide where to switch. The ITM51 replaces the ITM3. So if you remember the ITM3, it was around right up to about a month ago. The ITM51 is an improved version of that, has some more flexibility, has higher temperature limits, all right, a little bit different shape. It also has an easier to use display. You can orient the head differently, and we can even put a remote mount on it. We can also do some neat things with the output scaling that we could not do with the ITM3. For CIP systems, these don't really apply, but if we were going to go into some other applications, these things could be kind of handy for us. The other neat thing about the ITM51 is it's 10 times more sensitive than the ITM3. So if you look at these NTU, the methylometric turbidity units, we can take the ITM51 all the way down to 200, which is much clearer water than something with a turbidity of 2,000. So quite a bit more sensitive, so we can rinse even more of those solids out and be comfortable that we've done a good job of rinsing. And finally, well, not quite finally, almost finally, we've got the conductivity sensor in the return. So kind of like I was describing earlier, if we're sending wash chemical out, the only way we know that the entire circuit has seen that wash chemical is to monitor it in the return, okay? We could do some fancy stuff with timing and just kind of waiting on the wash water, saying, well, the chemical feed pump hasn't had to run in a while, must be my concentration is up to where I need to be, and it's all recirculating through. But now we're going to be wasting time. And what we're really after is the water coming back on the return line? Is it at the concentration I need it to be? Because as soon as it is, I can start washing with regard to concentration. So as soon as I see that wash chemical concentration on the return side meet the set point that's required, or the minimum conductivity set point, I can start my wash timer. If it's not at that point, I go into what's called conductivity hold, and I cannot start the countdown timer that says how long I'm going to wash. All right, so if we have low concentration, we're going to go into conductivity hold, and the wash cycle will not be started, and now we're just waiting on the chemical concentration to build up. All right, the ILM4, as I mentioned, can be installed as a remote mount. This is the new style, much like the ITM51. That's something we can do with the new platform. All right, and then again, the final thing is the temperature. So much like I'm sending hot water out on the CIP supply, I also need it to be warm or hot on the return. I cannot start my CIP wash timer until the return water is also warm. So I have to have concentration or conductivity, and I had to be warm. Both of those conditions have to be met. I need to maintain my flow rate, which is on the supply side. Once I have hot water on the return, I have chemical concentration on the return, my flow rate is established, now I can start my wash. And basically that means I start a timer that counts down for the certain amount of time that's been determined to be the appropriate wash time for that circuit. The water's not warm enough on the return. We just keep circulating hot water from the supply side until it reaches that temperature. And while we're doing that, we are in temperature hold, and the timer is not running. So again, TSM, TSB would be the sensor we would use on that CIP return. All right, so that was a lot of content in there. I know I went kind of fast, but we did cover the L3. We covered the conductivity sensor, which is the ILM4, the turbidity for the CIP pre-rinse, which is the ITM51, again, replacing the ITM3. We looked at a couple of flow sensors, the IZ-Mag for the return flow circuit and the FTS for return proof of flow, okay? And then the temperature sensor on both the CIP supply and the return. So definitely a lot in that presentation, a lot to look at, but what that basically means is if you've got a customer building a CIP system, or if you are building a CIP system, or if you've got an integrator building a CIP system, there's one place to go for the instrumentation, and that's Anderson-Negele. And with all these solutions, you're going to help your customer use less water, use less chemical, save time, and have a more efficient CIP process. Because as we said, CIP is just it's a cost to them, right? They want to get that process clean so they can go back to processing and generate revenue. All right. So that is what I had for you today. Sorry, I was a little rushed. But if we've got any questions, drop them in the chat or the Q&A now, and we'll address those. All right. I don't have anything popping up here today. I know I got into a lot of detail, and I know we're running a little bit long, so I want to thank you for your time. Those of you that are on this live, you'll receive an email for a PER code, and that PER code is going to be for an additional 5% off of any of the